welcome everybody. We are super happy to have Silvia Kusminskiy here today from the Max-Planck-Institute for the Science of Light in Erlangen, where she is since 2018. I tried very hard to Google her over the last 15 minutes, and what I found out is that she did her PhD at the Boston University in the Castro-Neto group in 2009. It was defended, and the defense note is still up. I also found her thesis online, which says that she did her master in 2005 in Uruguay, actually. So since her PhD in Boston in 2009, she, at least that's what I could find out, maybe you can correct me, what else happened. I know that she did a postdoc at the Freie University in Berlin, at least in 2012 she was there. And then she moved, I think, in 2016-17 to the University of Erlangen, which is very close to the Max-Planck-Institute. She has already given a couple of talks about probably similar topics recently at the Mainz University in the solid state groups and other seminars. So we are happy to have her again. Thanks for coming, and yeah, please give us your talk.
Thank you very much for the invitation, and also for the detective work. Yes, people complain about this. I should take care of having something up that actually yeah, so that people do not need to. Yeah, I will take care of this eventually. But thank you. You had everything more or less. Yes, is accurate. So I have nothing to add. Yeah, and I will be, yeah, so thank you very much for the invitation, and then I will share my screen. And as Anna said, so I've given this talk in a virtual format also, or some version of this talk in mind. So I hope, so I asked if there is overlap, and I was, I hope you haven't seen this talk already. So okay, good. So I will be let me go back. I will be talking about work that we've been doing in the last years in my group in Erlangen. This is basically applying methods of quantum optics to magnetic systems, and in particular to the magnetic excitations. And we've been, so we're a theory group, and we're basically interested in kind of pushing the boundaries of the state of the art, so proposing. You will see that we propose, say, things that we hope that can be measured or seen, etc., in experiments soon. So, oops, now I'm. Okay, so yeah, so as Arno pointed out, so we are a research group located at the Max-Planck-Institute for the Science of Light in Erlangen. This is us, so we are a theory group whose interest in the physics of hybrid quantum systems. And for you to have a more concrete idea, so a few examples of the systems that we are generally interested in are put in this slide. So basically, hybrid systems are those who can combine different degrees of freedom. For example, here there is an example of an optomechanical crystal that is designed such as light and mechanical vibrations can couple very well, or electromechanical systems where current can couple to the mechanical vibrations of this nanotube here. And what we've been working quite extensively in the last few years is a new kind of systems which couples, which incorporates a magnetic degree of freedom in hybrid systems. So the common denominator of these systems is, besides that they are hybrid, is their scale. So they are systems at the nano or scale or a few microns. That means that they are large enough so that one can think in terms of designing these systems, and in particular one is interested in designing their collective excitations, for example, how they vibrate. And also, on the other hand, they are small enough such that one can think in terms of, that quantum effects can be relevant. And then, so we are interested in understanding what are these quantum effects, and also in harnessing these quantum effects. So, on one side, one can think in terms of applications. So, in particular, in the speaking quantum technologies, processing, storing, and communicating quantum information. On the other hand, these systems are quite appropriate to investigate more fundamental questions. For example, how macroscopic can a quantum state be in the spirit of, so for example, Schrödinger's Gedanken experiment of the cat, which this is more or less the ultimate hybrid system in which something which is, well, alive or not is coupled to, but it's macroscopic, it's coupled to a really atomic and quantum system. So as I said, in the last years, we've been interested in hybrid quantum systems which are based on magnetic elements. So here is again a kind of collection of what are the systems that are being investigated nowadays. And the field is relatively new. So these experiments started maybe 6 years ago, but as you see, there is already a plethora of systems that are being investigated. So for example, here you see a magnetic element embedded in a microwave cavity. The same kind of setup can be used to couple the magnetic element to superconducting qubits. There are on-chip realizations that go in the direction of miniaturization. There are also experiments that probe coupling to other degrees of freedom, in particular, quite relevantly, mechanical degrees of freedom, and also coupling to optical photons. In most of these, not in all of them, but in most of the systems that I just showed, the material of choice is YIG, yttrium iron garnet. So this is what I'm just presenting it here. So when I said YIG, you know what I'm talking about. So this is a ferromagnetic, so it's a magnetically ordered material. To all the effects that I will be talking later, you can think of it as a ferromagnet. It is an insulator. So this means that this is it's a good material such that the excitations, the magnetic excitations, the magnons are quite long-lived. And it is a material which is transparent in the infrared, so that allows also to think in terms of magneto-optic effects. So what is a magnon? So now we have one has a magnetically ordered system. There can be excitations of this magnetic order. So this classically one sees that as spin wave. So this is the analogous of the mechanical vibrations, if you want, but instead of having the motion of the atoms in the lattice, here there is the atoms are fixed, but each atom or each unit cell has certain spin, and these spins will precess around their equilibrium position, and they do it in some coordinated way, and this forms as the spin wave. And the quanta of this spin wave is what we denominate as a magnon. So basically, a way of thinking about this is that a magnon is kind of flipping one spin, but this spin is flipped non-locally, in the sense that it's shared by the whole magnetic material. So it's a collective excitation, which involves a very, very a macroscopic number of spins. And the simplest mode, the simplest magnon mode that you can think about is the homogeneous one. So it has all spins are precessing in phase. So this is what you are seeing here. So just there is no internal degree of freedom, so to say. So there is a kind of a macro spin or a magnetization that just precesses with certain frequency. And this frequency can be controlled externally by a magnetic field. So why do we like these excitations? Where they inherit the very rich physics of the magnetic material, so they can be also used as a probe of the magnetic material. They are very robust excitations. As I said, also they are tunable, so one can tune their frequency, for example, with an external magnetic field, or also the shape of the Magnon modes by geometry. They are low power excitations in the sense that there are no ohmic losses associated with them, so there is no electronic transport associated with them, and they are a means to miniaturization, so one can pack them in very small systems. So, and also Magnons are friendly in the sense that they can couple to other degrees of freedom. So this makes them a kind of ideal candidate to incorporate this kind of hybrid systems, because they can couple very well in certain circumstances, can couple very well to electrons, photons, etc. And one can think in terms of designing this coupling. So in most of this talk, we'll be dealing with the coupling of magnons to photons. This coupling is in the as a rule quite weak. Then one uses the trick of enhancing the interaction by using a cavity, so a box for the electromagnetic radiation. And this not only can be used to enhance the interaction, but also it will introduce new effects or new physics to your system. So in terms of dynamical effects, for example, frequency shifts, induced dissipation, etc. And that on top of it, for example, one can think of driving the system. So I will be giving an overview of a few recent projects that we have been we have done recently in our group. It will be kind of an overview. I will not be giving too many details, but I'm happy to discuss at any point. Please feel free to ask questions. And I decided to divide it in two regimes, so to say. So magnetic systems coupling to photons in the microwave regime, and magnetic systems coupling to photons in the optical regime. And I hope that through the talk it will be clear why I made this distinction. So we start with the microwave regime, and just to give you an idea how this kind of started. So a few years ago, 6 years ago, there were several simultaneous experiments which showed strong coherent coupling between Magnon excitations in YIG, so this material that I showed you before, and a microwave field. So what you see here is a microwave cavity with this with a magnetic element, this magnetic sphere in one of the corners. As I told you, you can control the frequency of the fundamental Magnon mode here, the Kittel mode, by applying a magnetic field. So here is an applied magnetic field along the z-axis. For you to have an idea, tens of milliteslas give you a frequency of the Magnon excitations in the gigahertz regime. That means that this gives you a knob to tune the frequency of the Magnon mode, this Kittel mode, to put it in resonance with the microwave mode of the cavity. And this is what you see here. So then the modes hybridize and gap opens, and this is the indication of a very strong coupling in the system. So this coupling is, it's a resonant coupling, so the frequencies are the same, and it's due to the usual dipolar coupling. So the magnetization in the sample is coupling to the magnetic part, the magnetic part of the electromagnetic field in the microwave cavity. So you can see it as basically you create a photon by annihilating a magnon and vice versa. So this what you're having here actually is a magnon polariton, in which is a kind of quasi-particle, which is part photon, part magnon. So these seminal experiments, I would say, were followed by this experiment here, which caused quite a lot of excitement in the field, because they managed to show that by using this setup, they can couple coherently the magnon excitations in the magnetic sample via the microwave cavity to a superconducting qubit. And very recently, this kind of system has been used to demonstrate a single magnon detector. So this gives you an idea, or this indicates that the field is really going to this kind of quantum optics with magnons. So what we proposed recently in this work is that these systems can be, this experimental setup can be also used to generate very large states, cut states of the magnetization. So I'm going in the wrong direction. So, and our proposal is based on on a heralding protocol. So heralding protocol works such that you have 2 degrees of freedom, in this case, magnons and photons, and they will, so the idea is that you generate an entangled state, and then by measuring one of the parts of your system, you collapse the other system of interest in a state of your choice. So this is what we are going to implement, or like our proposal in this case. So what we need, if we compare what I showed you before, is basically the same setup, so a microwave cavity and a nanomagnet, but instead of having a spherical magnet that I showed you before, we need some anisotropic sample, as I showed here, so an elliptical nanomagnet. The anisotropy will create what is called the magnetization fields that will enter in the magnetic Hamiltonian. And so when you look at, so here is the magnetization, this is the magnetization factors tensor. So if you look at this Hamiltonian and now go to quantized language, so what you see here is S are the creation and annihilation operators of a magnon excitation. If you would have an isotropic magnet, so spherical magnet, you will only get this term here. So it's just basically a harmonic oscillator. Now, if you introduce an isotropy in the system, this the magnetization fields will cause, or the anisotropy will cause terms which are quadratic in the spin creation and annihilation operator. So basically, this is what is from quantum optics when it identifies as a squeezing term, and what it's now, if one looks at the ground state of this system, one will see that the quantum ground state is what is called a squeezed ground state. So the fluctuations, the quantum fluctuations on top of this state are anisotropic, as you see here. So this is compared to the, so if you would have an isotropic magnet, the fluctuations would be also isotropic. Classically, if you have an excited precessing magnetization, here what you would, the effect of this anisotropy terms would be that the magnetization precesses so there is an elliptical precession of the magnetization. So these are two phases of caused by or two effects caused by the same anisotropy terms. One is at the level of the ground state, and the other one at the level of the excitations. So now we take this Hamiltonian, which I showed you just for the magnet, and we introduce the microwave cavity. So now we introduce the cavity photons. So we have the harmonic oscillator for the photons, and now I have the cavity magnet interaction, as I showed you before. So annihilating a photon creates a magnon and vice versa, and the coupling strength is encapsulated here in this G. Now, this Hamiltonian is again a quadratic Hamiltonian, so one can diagonalize it and find also its ground state. And what one finds is actually that the ground state of this coupled system is an entangled state in which contains a finite number of photons and some flipped spins. So it's something that is that has some structure, if you want. And this is exactly the entangled state that we were searching for. So it's something that entangles photons and magnons. And now the idea is to do a measurement, and you want to measure the state of the microwave cavity photons. So what we showed is that if you perform, for example, a parity measurement in which you measure the cavity in an odd state, then you will collapse the state of the magnetic part into actually a cat state, and it's a squeeze cat state because, as you see here again, the fluctuations are anisotropic. So basically, one ends up with a state of the magnetization which is pointing simultaneously in two directions. So we went further to kind of characterize what would be the experimental requirements for this kind of cats and how large these cats can be. So can be measured in terms of this separation between the two magnetization directions. So what we find is that, so as usual, nature doesn't want us to see very large quantum states, but I actually for state-of-the-art experimental setups, and in terms of the coupling between magnons and photons, what we find is that if one goes to low temperatures, so in the cryogenic regime, this is possible to, it should be possible to create relatively large cats, which this R is around 7 or so. So yeah, so this, there are certain associated challenges actually in the, we think that the most challenging is probably the measurement of the state of the cavity, either parity or also kind of one needs a single photon measurement for the microwave cavity, which is probably, which is challenging. So I will move on now to the second example, if you want, and now I will be incorporating another degree of freedom which is present in the system, which is the mechanical degree of freedom. And this is a proposal in collaboration with a group of John Davis in Canada, in the University of Alberta. It's an experimental group. This is a theory proposal, but at the end I will show you some very recent experimental results from John Davis' group. So the idea here is to use these systems to perform quantum thermometry. So and for this, as I said, so one wants to also use the mechanical degree of freedom. So basically, we will use the coupling of the magnons to the photons in the system, and a way to understand this is by looking at the magnetoelastic energy of the system. So the system, the material we have will have certain magnetoelastic constants, And the coupling of so the magnetoelastic coupling can be seen in this expression. This is the magnetoelastic energy, and we see that the magnetization couples to the components of the strain tensor, which has information on the mechanical deformations of the system. One can proceed in a phenomenological way and quantize this interaction. And one will get many interaction terms, which is what I'm writing here. So here M are the Magnon operators and B are the phonon creation and annihilation operators. So depending on the frequency, so depending on what modes one is looking at, is which of these terms of the interaction will be relevant. Actually, for what I will show you now, this term is relevant. So a term which basically scatters two magnons from a phonon. So you annihilate a magnon, annihilate a phonon, and create a magnon, for example. So it's a parametric process. You need two magnons per phonon, and this is because the frequency of the excitations, so there is this mismatch in the frequencies. So the magnons are in the gigahertz regime, whereas the phonons in the system are kilohertz. So this is a kind of it's also called a parametric coupling. So now we have a system in which we have the microwaves. So we have the microwave cavity, which couples to the magnons as before. Now it's just I'm calling magnons with the letter M instead of S, which was before. And then we also have this parameter. So this coupling here is resonant. And now we have also the magnons coupling to the phonons in a parametric way. And this is, so they are in a bath of temperature T, and the idea is to measure this temperature T by noting that the thermal vibrations on the phonons will be imprinted on the magnetization. And this can be read off by doing basically noise measurement, so measurements of noise correlations in the output of the microwaves. So for this, one needs to drive the microwave field at a certain detuning. In particular, one needs to do it at a resonance with so actually at resonance of the bare frequency of the cavity photons and the magnon photons. And what we found out, what we find by basically solving the model, one needs to look at the quantum Langevin equations of motion, doing input-output theory. And what one finds is that there is a particular correlate. So if one measure a particular combination of the output noise correlations, one obtains a relation, as I'm putting it here, which relates these correlations to the temperature of the bath. But as you see, it has so all microscopic parameters do not appear here. It's just fundamental constants and the temperature. So this is basically what is called a primary thermometer, so something that does not require external calibration. So this is quite nice, and it's also the other advantage is that it's a primary thermometer which would work at temperatures below 1 Kelvin, and this is due to the fact that one is using a microwave. So that is measuring through this microwave cavity. So we also characterized the requirements, and one sees that there are certain sources. There can be certain sources of error to experimental imperfections, but we are confident that this can be a good setup to incorporate in experimental setups, so to actually do temperature measurements at such low temperatures, which is quite challenging. So, as I said, this is a theoretical proposal, but there have been some advances from the experimental side in the group of John Davis. So this is just an example of a very recent work that we just put a couple of weeks ago in the archive. So what you see here is a different kind of microwave cavity, and you see that there is this Higgs sphere is now here, kind of almost levitating. So it is free to move and just put it has only one point of contact. What in this work, what has been demonstrated is all the back action effects of the magnons on the mechanics. For example, one sees that what they were able to see is that what is called the Magnons spring effect. So a shift in the frequency of the photons, of the mechanical vibrations, due to the interaction with the magnetic system. And this is basically the first demonstration, or the first time that this has been seen so clearly. So there is not yet quantum thermometry, but the experimental setup is quite well suited for it. So now this was the microwave part. So I will change gears to go to the optical regime. So maybe I just do a small pause in case there are questions. And also I check my time. How much? I don't have time. No.
You don't have. You have time. You have time. You will not be interrupted. I promise.
No. I forgot we started at 15. So okay. So I thought we started at 2, and then I was very surprised. Okay. So okay. So the second part, as I said, is so the next few minutes I will be talking about coupling of magnons to photons in the optical regime, and just a short motivation. So if one will be able to couple magnons to optical photons, as well as one can do to the coupling to microwave photons, then this will be a very it's a very good candidate to have a quantum transducer, which is also tunable, so to transfer information from the gigahertz regime to the telecom regime. So if we think in terms of the coupling, how do magnetic systems couple to optics, we can think in terms of the Faraday effect. So if light is linearly polarized light propagates from magnetized material, its plane of polarization will rotate by an amount which depends on the Faraday rotation constant of the material and also the length that it goes through. Sorry, I need some water. And this can be encapsulated in the permittivity of the material. One can show that the permittivity acquires a term which is, well, to linear order in the magnetization antisymmetric. So this is the Levi-Civita tensor, and it's imaginary. So this is due to broken time reversal symmetry, and you have and this F here is basically related to the Faraday rotation in the material. So if now we look at what is the effect of, so now we have the permittivity, we can put it in the electromagnetic, at time average electromagnetic energy of the system. And this one will also acquire a correction due to magnetization, which is given here. So as you see, this is a correction which couples the magnetization in the sample with what we call the optical spin density. So these are here is the electric field part of the electromagnetic field in complex notation. So this E cross E basically is a vector that points perpendicular to the plane of polarization, for example, if you have circular polarized light. So as you see, now one can again proceed phenomenologically and take this interaction and quantize it. So we will get two photon operators from the electric field and operator from the magnetization. So this is again a parametric process, and it's again due to the mismatch in frequencies. So now we have photons that are in the hundreds of terahertz and magnons which are still in the gigahertz regime. So the coherent coupling between magnons and optical photons was demonstrated for the first time. So for this simultaneously by these three groups, and what you see here is actually now the same material YIG, which is it's the same, so it's a sphere, but in this case the material itself is forms the optical, so forms the cavities, an optical resonator. So the light comes in with an optical fiber, it goes inside, and so here it's a representation of whispering gallery modes in this spherical sample, and when it stays the light stays for a while here, and when it goes out, it carries information of the coupling to the Magnus, which can be measured as sidebands at the Magnon frequency. One way of seeing, so the coupling is weak, but one way of seeing that the cavity will enhance the interaction is a kind of intuitive, in the sense that since the light is spending a while inside of the material, basically the path that it goes through the magnetic material is larger. So this is a kind of intuitive way of thinking about it. So the issue is that even though there is an enhancement, the state of the art of the coupling and current experiments is quite small. However, we have shown that the theoretical limit is much larger than what is achieved nowadays. So the issue is the overlap between the optical and the Magnon modes. There is a lot of room to improve there, and also the systems they are still too large. One would like to really go to micron size magnetic elements. So the fractal limit, so smaller cavities always give an enhancement factor of basically 1 over the volume. So if one goes to these sizes in magnetic systems, it's so this kind of micron sized magnetic elements. So this is quite also interesting from the magnetic part, because basically a competition between exchange interactions and dipole-dipole interactions will turn in, that will give you ground states of the magnetization, which are non-trivial in the sense that they are not like all ordered like in one direction, but they form some textures. And the paradigmatic example, if you want, is a cylindrical shape in which the spins will order in a vortex configuration. So they try to avoid to point perpendicular to the surfaces. So this kind of vortex configuration has been seen in many different materials and cylindrical samples, including in YIG. So what we wanted to see is how, or what we wanted to understand is if one is has these magnetic textures, and one thinks in terms of how light couples to the magnetic excitation. So how does it work in the presence of magnetic textures? So now we have to go back to our coupling Hamiltonian that I showed you before, and take to preserve this the spatial variation of the magnetization. So we are going beyond what I showed you before this Kittel mode, in which all spins precess so there is no internal degree of freedom, so to say. So how we can treat this system in this case is actually consider small oscillations of the magnetization on top of a ground state magnetization, which is texture, so it has some dependence in position. And one can take this fluctuation, quantize it. Basically, one does, so technically one does a Holstein-Primakov transformation and cuts it to first order. And one was the way of doing this is what I show here. So one would get bosonic operators. Now I'm calling B the Magnon operators, which create and annihilate a Magnon in a basically Magnon mode function, or spin wave function, if you want, gamma. So all the information how the Magnon mode looks like is in these delta M's that you see here. So this is this is similar to what one does for the optical fields. So one can decompose the optical fields in the photon operators and in the mode functions for the electric fields. So if we put everything together, now we obtain a coupling Hamiltonian, which basically scatters a Magnon between two photon modes, which is what you see here. So a Magnon in mode gamma will scatter from beta to alpha, will scatter a photon from beta to alpha, and all the information on the coupling is in this G that I'm showing here, which contains the information on the overlap of these mode functions of the Magnons and Photons. So now the question is how to deal with this, how to calculate this coupling, and can we optimize it? So what we did, so to start with, is to take this paradigmatic example of a magnetic vortex and look at how photons in whispering gallery modes, which can also be present in these cylindrical structures, coupled to Magnon modes on these magnetic vortices. For this, usually one needs to resort to numerical simulations. We used actually this system because in certain limits, one can also do analytical progress. So we had a way of benchmarking our numerical results, but in general, one needs to find the Magnon modes doing micromagnetic simulations. So this is what we did, and we used finite element simulations for the optical modes, and then to combine them to find the coupling. So just show you as a small example. So this is how a vortex core looks in a magnetic disk when it has been displaced by an external magnetic field. So these are different. So this is the core that kind of snakes through the disk, and these are different sections of the magnetic texture. So this is actually the ground state calculated with micromagnetic simulations, and on top of it, one can calculate the Magnon modes localized at. So what we were interested in are Magnon modes localized at the vortex core, and this is what you see here. So these are basically kind of so flexural modes. So they are kind of modes of a string, but actually so they look like modes of a string. So it's like the vortex core is it's like a magnetic string, if you want. And we used our method to calculate the different the coupling to photons to the different Magnon modes. And as you see, so there is an optimal mode, or a mode that couples much better than the others, and the coupling we obtain something in the range of kilohertz, which is it's quite promising. So if one looks at the cooperativity, it's still, so the cooperativity gives an idea of how large the coupling is to the dissipation channel. So this will give us a cooperativity of 10 to the minus 2. It's not, so one would like to be about 1, but this is anyways orders of magnitude larger than what is currently done or has been achieved experimentally. So this gives an idea that it's promising. So these systems are promising in terms of if one designs the excitations, one could achieve much larger couplings. So this is what we turned to do next, and this is basically the last 2 minutes. Let me present our latest work on this regard. So we were inspired by the success of optomechanical crystals, and we said, okay, can one design a system which is an optomagnonic crystal, so a patterned magnetic dielectric with which is patterned into a kind of a periodic structure, and with a defect such that it can co-localize optical modes and Magnon modes to improve the coupling and diminish losses. So we use the same kind of techniques that I showed you before, so using micromagnetics to calculate the Magnon modes. In this case, however, one needs to take into account that we are working with periodic structures. So basically one needs to look, well, we're looking for localized modes at the defect, so that they fall in the band gap for the optics and also for the magnetics, and that the symmetry of the modes match such that one ends up with a finite and hopefully large coupling. So this is what we did, and what we find is that actually this simple geometry, so we started with a simple geometry to try to understand how the Magnon modes look like. So what we found is that this is again looks quite promising. So one can find Magnon modes that have the right symmetry. They have to have there's actually the symmetry of the optical spin density, and so we can see that so the coupling, for example, that would depend on the height of the structure, and also one can optimize or slightly optimize the structure to obtain larger values of the coupling. It's a promising route, but again, these kind of structures turn out to be quite lossy for the optical mode, so further work is needed in this respect. But it's again, it seems promising from a theoretical point of view. Is promising in the sense of what kind of values of the coupling can be achieved. However, there is also the issue of the experimental implementation, that there are issues yes, on how but I'm not an experimentalist, so so there seems to be issues on patterning, in particular Higg, in this kind of crystal shape. So then I will leave you with the outlooks. I hope I convinced you that so the state of the art in the microwave regime is already quite advanced and ripe for doing things in terms, for example, of generation of macroscopic non-classical states, and also to use these systems for applications in, for example, in terms of quantum thermometry. At the optical levels of coupling to optics, actually the it's a kind of urgent issue, I would say, to look at how the coupling values can be improved, such that one can think in terms of, well, in terms of applications. So this is why we've been also looking a little bit into how to design the structures and developed a method for doing this. So I thank you very much for your attention, and also the funding agencies, and I'm open to questions. Thank you very much.
Thanks a lot for this super nice talk. I'm clapping and I'm throwing confetti up. So I'm sure there are questions. If you have questions, you can raise your hand either via Zoom or in person with a camera on, like Ferdinand just did.
Yeah.
So maybe we start with Ferdinand. Go ahead.
Very much for the nice talk. And my question is, there are these cantilever structures which have bending modes. And the question is why you take this type of structure with holes. That is a photonic and phononic waveguide. Yes, I know. But would be just a cantilever not bend much more, and then you could make this coupling larger?
Okay, but so the structure that I showed is not. We are still not. So the modes. I didn't look at the mechanical modes. I looked at the magnetic modes.
Okay.
And but you are correct that one could also, and this is something that also we are thinking on. So this one could use also this to have a structure in which there is also a mechanical degree of freedom. And then one can think in terms of also
enhancing this by a clever design. Yeah.
Exactly, or maybe even just to go to use basically the best of all coupling, so to say. So maybe photons coupling good to phonons, and phonons coupling good to magnons is better than a direct coupling between photons and magnons. But we haven't. Yeah. So this is we actually we looked a little bit at these things, but so basically, this is we look first at the coupling between magnons and optics.
And then I have another question about the size of this little ball, which is showed in one of the first transparencies in the cavity. Yeah, what limits the sizes? Actually, I think if they are larger, the coupling would be larger. Yes.
So that it's actually what you okay. So first of all, the sizes of these spheres that I showed, they are still pretty large. So I think now people can work with maybe 100 microns. The thing is, apparently YIG is a quite nasty material to pattern, and in particular to do spheres, because one will need very nice and well polished spheres. So to make them at the very small sizes is difficult from an experimental point of view. So these sizes, the spheres that I showed they are quite large. Now, ideally, one wants two things. First, an optimal mode matching, and between either microwaves or optical photons and the Magnon modes, and small volumes. So it depends. So you always have this. So the volume mismatch always goes against you. So you are correct in the sense that so if you will have larger spheres in the microwave regime. So in the microwave regime, you are in a regime in which your photon mode is much larger than your sphere, and then you want to make either you make the sphere bigger or you make the microwave mode smaller. So
Yeah.
And this is what the people in these on-chip realizations, which I showed you, did. So in these on-chip realizations, they managed to, they confine the microwave mode to a very, very small size because they have the circuit implementation. And this gives them a very, very large coupling because they have a good overlap, small volume, and they have more dissipation, but actually the coupling is so large that they don't care.
Mm-hmm. Thank you.
Yeah.
There's another question by Ahmed.
Yes. So I was just wondering, when you talked about the coupling, the optical coupling between the magnons and the photons, you said like you get the photons to, or the light to spin sometime inside of the cavity.
Mm-hmm.
So how do you get this to happen? Because I didn't quite get this.
So yes, so basically the material is an I didn't explain this. So the material is an it acts as an optical resonator. It has an index of refraction of around 2. So basically it's a dielectric. When the light goes in, then it's trapped inside by a total reflection. Yeah. So it's just a dielectric with an index of refraction larger than 1, and it just confines light. And then but at some point it will, of course, the modes are leaky, so at some point the photon will go out.
Okay, and another question is, don't you have a thermal effect on the coupling usually? Because this would change the states of the magnons. I mean, the spin waves would be affected by temperature, wouldn't it?
Well, the thing, what I showed you is the coupling per. So I was always talking about coupling per magnon per photon. So the thermal occupation. So you can have a thermal occupation of the magnons, and you can drive the system such you can put many magnons in your mode, but what is, if you want, in what the interesting number is the coupling per magnon, right? I'm not sure if this is your question.
My question, if you go, for example, to very low temperature, would this enhance your coupling?
No, because the coupling is independent. Okay, except for, I don't know if you have deformation, but to first order, the coupling is independent of temperature.
Okay.
Because I think so. What you will have from thermal effects is that you will have, for example, you can have a finite occupation of your magnon mode. So you can have, you have some Bose-Einstein number you have some finite occupation of your mode.
The density, you mean, of magnons?
Exactly, but if the coupling that you care about is the one per magnon, right? Unless if you have a parametric coupling, so then you can enhance also the coupling by basically by the square root of the number of magnons. So if you look at the coupling to phonons, this is also done. But then there you don't want the thermal magnons. There you want really a coherent, a steady state. So you want to drive the system and to have some coherent state of magnons with a certain average steady state number of magnons, and then your coupling will be enhanced by the square root of this. In the case of the coupling of magnons, parametric coupling of magnons to phonons. But yeah.
Thanks.
Cool. I'm sure there are other questions, but let me, while we are still more than 20 people, announce next week's quantum seminar. It is called Terahertz Quantum Sensing, and will be given by Professor Georg von Freimann from the Technische University in Kaiserslautern. Are there more questions? Maybe I ask a question. I mean, you probably explained it already, but yeah, maybe you can explain it again if you haven't. So, I mean, the mode structure, the higher order Magnon modes. I mean, in the later part of your talk, you sort of talked about it, and then you showed even a couple of higher order modes, I thought, and then I was just wondering where the frequency comes from and whether the frequency still, I mean, it should still be given by the magnetic field, no?
Okay.
I mean, is there a higher order frequency shift, and what is the shape of higher order Magnon excitations?
Actually, so this is a little bit different. So you see my screen, right?
Yeah.
So the frequency of, so if you, so the simplest, maybe the simplest way of looking at this is, so if you have a magnetic vortex without, so don't think about an external magnetic field. Then you will have some, the vortex will be in the middle, okay? And then there is one kind of special mode in this Magnon mode in this system, which is called the Geotropic Mode, which is you displace the vortex core from its equilibrium position, and it will start rotating around the equilibrium position. So this is basically okay, and the frequency of this mode is actually, it depends on the aspect ratio of the disk, and it's basically 100 megahertz or so for a micron-sized structure. So this, yeah, this is in the megahertz range, and then there is, so you have, this is basically in a Magnon band gap, and then after, so in gigahertz frequencies, you have other extended modes like spin wave modes that look a little bit like a membrane mode. So if you would have a drum, so this kind of modes. So so basically the frequency of the mode we are looking at is basically determined by the geometry and the aspect ratio. I think you are right. There is a small dependence on the magnetic field, but I don't remember. We have it in we have it in appendix in our paper, but I don't remember right now what is. It might be. I don't remember the dependence. I think there is some dependence on the magnetic field, but I just don't remember how strong this is. Yeah.
Okay, yeah, it's just like because the material is still the same, or the constituents are still the same. I mean, they have electron spin Larmor frequency of 28 gigahertz per Tesla, or not?
Yes. Yes. But this kind of so this mode, as I said, so it's a little bit different. It's this geotropic mode, which is basically, if you don't consider an external field, basically is the idea is that this mode, you can look at it as if it would be the vortex core like a particle. The charge of the particle is actually the topological, so the half Skyrmil, so the Meron number, or Skyrmil, so half Skyrmil number of this topological object. So it has some kind of topological charge, which couples to the magnetic field of generated by the magnetic texture. So it, yeah, basically it's it's determined by the magnetic texture, which is in turn determined by the geometry. And so at this level, there is no, so you still have a finite frequency of your mode, which is, yes, as I said, in the so a few megahertz, depending on the size. And yeah, and then if you apply a magnetic field, you're right, there is some dependence on the magnetic field, but it's not, it will not take it to, so you see here you have a millitesla's field, but still the frequencies are in the megahertz regime. So it doesn't take it to the dependence is not as the one of the Kittel mode, which will give you gigahertz regime. So it's a different kind of mode. Yeah.
All right, thanks. And who's building your systems in the Max-Planck-Institute?
Well, so actually, so the Max-Planck, so what they, as I said, there is the issue that this YIG is very hard to pattern. So initially, they were trying to. So first, the experimental groups, they tried to get YIG microspheres, and then when they got them, it turns out that the microspheres are more like micro potatoes. They really don't. Yeah, they are not spherical at all, and. Yeah, so then there was a bit, so fabrication is a bottleneck. So then, so I think there is one person in Erlangen that can grow this. So they are trying, I just don't remember her name, that they are trying to actually grow the structures. And then there are, so in Halle, there is the group of Georg Schmidt, who they basically they are the ones that can actually pattern very well YIG, and they actually have demonstrated, for example, suspended structures that go in the direction of what I showed at the very end, this kind of bar structure that then one could in principle pierce with holes. But yeah, so fabrication is, as I said, seems to be something very difficult. But yeah, I'm just repeating what the experimentals tell me.
Yeah, they're always just complaining experimentalists, right? Okay, are there any last questions, maybe? This doesn't seem to be the case, so thanks a lot for the really interesting talk and for the cool physics. I enjoyed it a lot. And then we can close this session of the Quantum Seminar. Thanks a lot, everybody.
Thank you very much.
Thanks, and thanks for the invitation. Bye-bye.
Yeah, bye.
Bye.